Okay, so if there are no questions, I'll proceed. Okay. So let me remind you that last time we look at the spectrum of type 2 and type 2 string theory. And the main feature that we learned is that if we take NS, this gives you bosonic. NSR gives you fermionic. RNS gives you fermionic. And RR gives you bosonic. So what is not obvious from this analysis is that if we look at the spectrum for any given mass square, okay, so the full string spectrum has states of all possible mass square, all mass squares, right, in integer units. Okay. For any mass square, okay, one can show that the fermions and bosons form a degenerate pair. So for every mass square, there are equal number of fermions and bosons. This is not straightforward to see in this RNS or Ramon-Navus formulation, okay? But later on we'll describe, okay, how to find a map between the states from fermionic sector to bosonic sector. Okay, but it's certainly not obvious from what we have said that there should be degeneracy between the fermions and bosons. Okay, but you can check at every mass level that this is true. When you impose the physical state conditions, you have exactly the same number of states, which are fermions and bosons.
This indication of supersymmetry.
Yeah, so this is an indication of supersymmetry. So this is a necessary condition for supersymmetry, but certainly not sufficient, because the full supersymmetry requires that all interactions are also invariant under supersymmetry. Okay, but again, we'll see how we prove it in general. Another feature of the spectrum that should be obvious, and this is also true for the bosonic case, is that on any given Hawk vacuum, because once you have chosen a K, then the left and the right sectors can be independently constructed, right? The Hilbert space on the left and right sector, the full Hilbert space is a product of the Hilbert space on the left and Hilbert space on the right, right? Because you create the Hilbert space on the left by using the alpha tilde oscillators, alpha tilde and b tilde oscillators, and you create the Hilbert space on the right by using the alpha and the b oscillators.
This is when you consider all these four sets.
Yeah, so this we can write as this is again for a given fog vacuum, right? That Ns plus R times Ns plus R.
After putting physical state condition, we get.
Yeah, so even in the physical state condition, right? For given K, the LNs and GNs are in the right sector, and LN tilde and GN tilde are on the left sector, right? So they are independent conditions. So for any given K, the physical state conditions are also independent. Right? So you can construct, so this means that you can construct for any given K, you can construct first the physical state spectrum on the left, the physical state spectrum on the right, and then combine them together.
Physical conditions are level matching.
Yeah. So recall, where does the level matching come from? Right? The level matching comes because we have the left right sector. So let's consider a state of the form alpha mu minus, right, product over I mu, sorry, n mu. Times the fog vacuum. A, and then you can have A and B. Okay, these are only in the Raman sector. Okay, in the Nebu sector there is no label, right? So no label and A times no label and B. Okay. And then the level matching condition is that alpha prime K square by 4 plus sum over mu and n equal to C. And alpha prime K square by 4 plus sum over mu n R and mu. Right? So these are independent of each other. Right? For a given K.
Yeah.
Right? For a given K, it fixes this combination and this combination. Okay? The label matching condition comes because it's the same K that appears in both expressions, right? So that's why the left and right get related. That's why you can eliminate K from here and say this equal to this, and with C minus C tilde. Is this point clear? Right? So for a given K, the spectrum can be constructed on the left and right sector independently. But because it's the same K that appears on the left and right, yeah, then you can eliminate K and get the level matching condition. Right? So level matching condition comes after eliminating K. Okay. No, this is also true for bosonic string.
Alpha mu minus 1.
Yeah. So there also it's exactly the only difference in bosonic string theory is the last term was not there. Yeah. So what I'm saying is that, yeah, there it was alpha mu minus n to the q mu n, alpha tilde mu minus n to the r mu n. These things were not there.
This statement that any state is like product of alphas and alpha tilde states.
That's what it is, no? Because q mu n can be chosen arbitrarily. Yeah, why was it not allowed? If it was allowed, you could have chosen this to be 0 and this to be non-zero, right? That is a level matching condition. That condition, the fact that the only alpha mu minus 1 was not allowed, right, was because of this condition that the same K cannot satisfy both. Right? But for given K, if you think of this as what kind of Hilbert space you have for a given K, right, then you have factorization. Right? It's just that for most Ks, right? You cannot satisfy both these conditions. Is this point clear? So indeed, eventually the Hilbert space is not factorized because we have to make sure that the same K satisfies both, right? Okay, that's what connects the two, right? That's why by eliminating this K, you get the level matching condition. Exactly, that's this. Because for a given K, it is true. If I keep a K fixed, right, and create the states on the left and right, yeah, you can independently apply the operators, and these, when you wrote down this condition, right, we didn't have to say anything about the right, about the left sector, right? And when I wrote this condition, we didn't have to say anything about the right sector.
Yeah, the constraints are also independent.
Exactly, right? So suppose somebody has given us a K, okay, and I'm trying to construct the states on the left and right. I can construct them independently and take the product, right? That's what I'm saying here.
You said eventually it is not factorized or something.
Yeah, because eventually, if we eliminate K from here, you get a level matching condition, where the same K both has to be satisfied, right? So imagine that, suppose everything was 0. Suppose C and C tilde was 0 and K was 0, right? Then you will have a condition, sum over this plus this equal to 0, and then sum over this plus this equal to 0, right? So do you call them, say that it's not factorized? Because both sides have to satisfy independent constraints, right? Okay, it is still factorized. You construct the state on the left, satisfying the constants, construct the state on
Hello. Hi. Uh, the, can you hear me?
from there. Right? That the spectrum can be constructed independently. Okay, for a fixed K, right, you can see from this structure, no, because you have the products on the left and right, over the left and right, and you have these conditions independently.
I'm still slightly confused what in NSNS sector, if I apply odd number of these,
Yes.
why shouldn't I call that a Fermionic?
If you apply odd number of these, no, that's not a Fermionic. That's GSO, that's a GSO odd, or that's actually GSO even. So that's not a Fermionic. Fermionic is an RNS sector.
By definition, by the number of these.
No, RNA, because they carry spinor index. From the space-time perspective, right? Yeah, so these are all space-time. From space-time perspective.
For Grassman parity has to do with,
That has to do with the GSO.
but will that decide that it will be in NSR sector we can have worldsheet Grassman even parity, right?
Yes, but you have to fix that convention once and for all, right? That you see, pick the vacuum, right? Say carrying index A as the GSO even vacuum state. Then odd number of odd number of B's acting on that will give you Grassmann odd state, right? Not Grassmann odd, the GSO odd state, and even number acting on that will give you GSO even state, right?
How will that reflect in the whether it's a Fermion or not?
No, it is always a formula. From a space-time perspective, once you have Raman sector, it's always formula. Either the GSO odd states are projected out; they are thrown away from the spectrum.
So that statement is equal to saying that if you put say the boundary conditions on the worldsheet side, you get bosonic spectrum on the target.
In the target space, exactly. Because Raman sector, you have seen carries spinor index, no? The vacuum. And once the vacuum carries spinor index, right? Exactly. Any operator that you have, right? B's and alphas, they don't change spinors to vector-like representation, right? They always keep it as spinor. So all states in the NSR and RNS are Fermionic.
And the same student RR has two labels.
Exactly. RR has two spinor levels, so the product is bosonic.
The vacuum you're saying has a spinor index because the vacuum must have some C's and gammas along with it. Is that so?
No, because VC is not the vacuum we saw, there is a zero mode, right? B mu 0 is there in Raman sector. When you quantize B mu 0, right, it becomes a Clifford algebra, right? And the representation of a Clifford algebra are spinors or space-time, right? So the B0 quantization requires that the Raman sector ground state has spinor. Right? And once our ground state has spinor, then any oscillator acting on that will keep it in the spinor representation. So do you agree with this or not? Why is this shady? I mean, this is perfectly good. I mean, you have factored Hilbert space, right? Right?
This statement very profoundly.
Yeah, we'll use it. I mean, not profoundly, maybe. I mean, it depends on your degree. I mean, your yeah, what you call profound, right? But the first thing we'll use it for example, that the supersymmetry that we discussed, right? Space-time supersymmetry, not worldsheet supersymmetry. This is space-time supersymmetry, indication of space-time supersymmetry. Worldsheet supersymmetry, of course, is something we started. So this one can be seen separately on the left and right. Yes.
You're saying this is purely an indication, but we have nowhere shown that target space theory is
Supersymmetric. Yeah. For that you need the interactions, right? But just let's look at the spectrum. Right? Spectrum of the target space theory is supersymmetric. Okay? So the claim is that the space-time supersymmetry that I discussed here, right, acts separately on the left and right. That there is if we just look at the spectrum on the left, right, then at every level there are equal number of bosons and formulas. Okay, fix K, okay, and look at the spectrum on the left. So let's take NSR. So what does it mean? NSR.
Worldsheet supersymmetric theories that don't have a target space.
Yeah, there are.
So what happens to the
Worldsheet supersymmetry is quite different from target space supersymmetry, right? They are a priori not related to each other, right?
But does the worldsheet theory have some special property? Sorry, does the target space theory have some special property because of the worldsheet?
Yeah, I mean they are different from the standard bosonic string theory. They'll still have the Ln and Gn projection, right? Gn projection is not there if we didn't have worldsheet supersymmetry, right? So Gn projection will be there, but it's just the spectrum is not supersymmetric.
The matter T equal to 0 at the G because of the super part of the action equal to 0. These two conditions.
Yeah, exactly. Yeah. Right. So just like we had Ln acting on the state equal to 0 condition for positive n, we also, yeah, more sub G also will have to highlight it if you have worldsheet supersymmetry.
Also, in after you use the
Yeah, after you impose level matching condition. So you have k square. So this condition has to be satisfied. Also, all the ln's and gn conditions have to be satisfied. Okay. But after you satisfy that, okay, you can forget about the right sector altogether, right? So take NSR and RR. You don't care if this is R or NS. Okay. Yeah, on meaning we are just looking at kind of spectrum, right? Not we have not talked about interactions at all. At the level of the spectrum, okay, the claim is that in any level here, okay, you can see that the number of NS sector states and number of R sector states match. Okay, for any particular state here, you take any particular state on the right sector. Okay. Then the number of states in the NS sector and R sector will match for that particular state. Whether it's R or NS doesn't matter, right? Because we can solve for these two conditions independently. Right? For a given k, we can solve for these conditions independently, right? That fix a k, okay, and now look at solutions to this equation, okay, for any particular values of these. Total number of fermionic and bosonic states, the total number of spinors and vectors, spinor-like states and vector-like states will match, right? Which means the total number of states in NSR is equal to total number of states in RR.
This statement is after you impose all the conditions.
After you impose all the conditions, okay? But because all the conditions can be imposed independently on the left and right, right? So this statement is true, but for a given k square, I mean after you impose all the conditions. Yeah, exactly, right? But for that, you don't even have to look at this right part at all, right? Just look at all the solutions to these equations, right? In the NS sector and R sector. Those two are equal. You can check that. I have not proven it, right? But you can check that this is true. The which? Yeah, here is U and V. See, these two are R and V, right? These are the left sector oscillators. These are the right sector oscillators, right? I am saying that pick any particular combination R mu and V mu. Okay, doesn't matter. For that state, just look at the left sector. Okay, so left sector, NS sector will give these acting on the vacuum, and the R sector will give you these kind of combination with R being now integer instead of half integer, acting on those spinor states, right? Spinor vacuum. Okay. After that, you do GSO projection. Right? That can be done again independently in the left and right. After the GSO projection, you will find that irrespective of what you have chosen here, okay, just the number of solutions that you get for these kinds of states are the same that in the fermionic states and bosonic states will be the same.
So this statement is equally true for R and S and NS?
Yes. So this is equally true for RNS and NSNS.
And you can also keep the first one the same. Do this on the right.
Exactly. That's what you are doing here, right? This is on the, you are doing, what did I do? Oh, this is the same. Yeah, exactly. So this is true. So both, this is also, this is on the left and this is on the left. Right? Similarly, in the right, we can do NSR and NSNS. So these will match. And then RR and RNS. Okay, these will also match. Okay, so the spectrum in this sector will be equal from in the left and right sector. Sorry, will be equal in the spinor and vector-like representation. Spectrum in these two sectors will be the same. Spectrum in these two sectors will be the same, and the spectrum in these two sectors will be the same. Okay, that's the claim that this equality between the number of bosonic states and number of fermionic states, it can be tested independently in the left sector and the right sector.
At the end of the day, you just want to write a left supersymmetry and right supersymmetry.
Yes. Right. So this is saying that there are essentially two supersymmetries. Right. One acts on the left, one acts on the right.
Target space.
Two target space supersymmetries. Okay. So this is the reason why these are n equal to 2 supersymmetry. There are two supersymmetries. Right? N equal to 1 will be in that there is only one supersymmetry.
This two sucies is the fact that you can do it either on the right or on the left.
Exactly. That you can do either on the left or on the right. No, target space there is no left and right, but you can divide the target space fields into these four classes: NS, NS, NSR, RR, and RNS, right? So the first supersymmetry relates NS, NS states to RNS states. Okay, without worrying about the other sector, right? It relates NS, NS states to, so the first supersymmetry no, not fourth supersymmetry. The first supersymmetry relates NS, NS to RNS and NSR to RR. It's the same supersymmetry, right? If you take a NS sector to RNS sector, right, the same supersymmetry will also take an NSR to RR. Okay, so that's one supersymmetry.
The left thing is left.
Left thing is left, right thing is right. very simple convention. Yeah, this is like something like left SUSY. No, it can't take the first supersymmetry cannot take NS, NS to RR. Yeah, it will be composition of two, right? So the second supersymmetry will take NS, NS and NSR and RNS to RR. So if you want to go from NS, NS to RR, right, you have to apply the first supersymmetry first and then second supersymmetry. Right? That will take you from NS, NS to RR.
So there's a total of four. So if I think from the worksheet, target space perspective, there's a total of four
Sectors.
classes of states, four sets of
Four
states.
classes subsets.
And there is a supersymmetry relating two of them, and another supersymmetry relating another two of them. That's why should we-
Yes, but two of them don't. Yeah, you can think of it that way. Yeah. Yeah, exactly. So it takes 1, 2, 2, 3, 4, the first supersymmetry, right? And so, sorry, if you take 1, 2, 3, 4, right? The four classes. 1, 2, 3, 4. If you want to think of it that way, right? The first supersymmetry relates it like this, right? The second supersymmetry relates it like this. Okay, maybe I use some other symbol.
So that would have been more. N equal to more.
In principle, but that isn't. Right? I mean, the supersymmetries that we can see, right, are just two. One acts on the left sector of the worldsheet and the other acts on the right sector of the worldsheet.
But there's a cap. I mean, it's not like any amount of supersymmetry I can have. I can maybe go to 1, 2, 3.
Yeah, but what he's saying is that, I mean, why n equal to 1? I mean, the left sector itself, there may have been more than one way to arrange things, right? See, one supersymmetry basically means that it's really 16 supersymmetries, 16 different transformations, because supersymmetry transformation parameters are also spinors, right? because it's relating a vector-like representation to a spinor-like representation. Right? So a supersymmetry generator itself will carry a spinor index. Okay, so n equal to 1 means 16 supersymmetries. Right? Because the spinor index of SO9, 1 is 16 dimensional.
This is 2 to the what? 2 to the 4. 2 to the 8 by 2.
2 to the 8 by 2, yeah.
It could have been more, right?
It could have been more, yeah.
If the spectrum was more.
Yeah, it could have been more. But there is a general theorem that you cannot have more than n equal to 2 just by analyzing the algebra, because you have to make sure that supersymmetry algebra and the Lorentz algebra closes. Right? Using that one can argue, but this is a completely different analysis, right? Just at the level of the algebra, that n equal to 2 is the maximum you can have in 10D. Yes. Because if you look at the spinor representation, right, you will think it's 2 to the 5 by 2. Sorry, 2 to the 5, right?
10 by 2, yeah.
10 by 2. But then you can impose a chirality condition, right? And that reduces to, so from 32 you come down to 16. Complex, yeah, supersymmetry, I mean, in 9 plus 1 dimension, you can have Majorana-Weil spinors.
So, but
Real supersymmetries. Yeah, so 10 real, 16 real supersymmetries. Yeah, they don't act on the modes, right? They act on, because they are, if they acted on the modes, they'll never take an NS to R, right? They are taking the NS sector to R sector. So if you recall, the NS and R from the worldsheet perspective, right, are built on different ground states. Right? And it is taking from one ground state to another ground state. Right? So you cannot represent the supersymmetry algebra, the supersymmetry generators, in terms of modes. Right? Unlike Lorentz generators, for example, right, which acts in a given sector of the worldsheet, and you can write them down explicitly in terms of the modes. Yeah, so NS vacuum, for example, is GS odd anyway, right? It's projected out. But if you take the first GSO even sector, right, which is B mu minus half acting on the NS vacuum, right, that changes to one of the Raman vacuum under supersymmetry. And because both of them represent massless states. If you recall, B mu minus half acting on the vacuum and the Raman vacuum, both are massless states, right? And they are related by supersymmetry.
Can we write down the generators?
We can, but for that you have to introduce spin fields, which I have not done, right? Which we will do. Not in terms. You cannot write down the generator in terms of these modes.
No, but in principle, since I know the full Hilbert space and I know the matrix elements of the supersymmetry, I can just explicitly write down.
Yeah, as a matrix you can write down, right? But what he's asking, you can write them down in terms of these modes, right? Just like you write a Lorentz generator, right? Because it's changing from one vacuum to another vacuum, right? So that you cannot do in terms of the modes, right? Normally, if you have a spectrum built on one particular vacuum, right, then you can try to write down the generators in terms of the modes.
Just that oscillators don't relate different.
Exactly. Oscillators don't relate the Raman and Raman-Schwarz vacuum. Right? So you have to find some extra operator that takes you from a Raman-Schwarz vacuum to Raman vacuum.
But on worldsheet we have this, what do you call it, twist off?
Yeah, so it will be like spin field which will twist it. Right? It is not writable in terms of the oscillators. Is this clear? So that vacuum is the target, is the target space vacuum. Not the target space vacuum. I mean, that is like a multi-particle state. I mean, in target space, you'll think in terms of multi-particle state, right? Multi-string states, or target space vacuum will be when there are no strings. So obviously, you cannot write them in terms of the B's right? Because target space vacuum has no string.
People know what the target space vacuum is.
Yeah, in the absence of strings, right? When there are no strings, that's the target space vacuum, right? Just like in quantum field theory, right? So think in terms of this as a field theory, okay, whose single particle states are all that we are studying. Right? If you want to think in the field theory language, right, what you are studying is the single particle state of an underlying field theory, right, which is a string field theory, which will have its usual structure, right, single particle, multi-particle state, no particle state, and so on.
But vacuum is string creation operator.
Yeah, so in string field theory, there will be a string creation operator.
You're saying you're studying quantum mechanics of a string.
Yes. So this is like a one particle state in string field theory. Right?
But Hilbert space is like once and for all, right?
No, this Hilbert space is a single particle Hilbert space. Right? Here you are counting electrons, muons, protons, right? All the single particles, even not even protons. Protons are composite. Right? There's electrons, muons, W bosons, and so on. Right? But then the full Hilbert space can have one electron and one W boson, right? That is not in the spectrum. Because if you have one electron, one W boson, right? K can be continuously variable, right? Total momentum of an one electron, one W boson state is not discrete. That is familiar? Right? There's a Marshall condition, right? So the very fact that you are getting some K square equal to some discrete value basically shows that it's a one particle state. And if you didn't have any electron or W boson, zero particle state, there will be no K. Right? So what you are studying really, I mean, so that you should keep that picture in mind, right? What you are studying here are single particle states in the quantum field theory.
The standard perspective, that is a bit misleading. Like for instance, proton does have a one-cell Marshall condition.
Yeah, but proton is composite. Exactly. Yeah, it has a Marshall condition, it's composite, right? So in this language, it will be called this. These strings can bind. Once you introduce interactions, the strings can bind and give rise to proton-like things. Right? That's also not part of this, because this is only giving the fundamental particles of string theory.
It sounds like we're just doing free.
Free, exactly. The free field theory of a string field theory, and the single particle states is what we are constructing. Okay? But in the free theory, of course, you know that once you have the single particle states, you can easily construct a multi-particle state, right? With the understanding that if you have multiple fermions, they'll have Grassmann odd creation operators, right? You cannot create more than one fermion in the same state. So the same kind of rules will apply there for constructing multi-particle states.
Why do you say that space-time vacuum will be some multi-particle state?
Space-time vacuum in a free theory will be no particle state, right? But in an interacting theory, the space-time vacuum itself can be complicated, right? Like the QCD vacuum, for example, right? It's a complicated object. You have to find a ground state of that interacting theory. It's clear? Not clear.
So interacting string theory, we don't know the vacuum.
Interacting, okay, perturbatively interacting string theory in 10 dimensions, we do have some idea about the vacuum, because there you know that you can use perturbation theory, right? This theory, if you introduce interactions, and if you work at a weak coupling limit, right, you can show that the perturbation theory is a valid approximation there.
So the vacuum is without any string, and then
Yeah, so you still have corrections, right? Just like in LSD formalism, the vacuum itself has to get corrections, but those corrections can be studied perturbatively, just like in a quantum field theory. Yeah, exactly, right? So you'll have all those bubbles. Yeah. So interacting vacuum will have all those bubbles. Okay, so this is also sometimes referred to as 1, 1 and 0, 2. This is for 2A and this is for 2B. Yeah, I'll explain what I mean by 1, 1. So the difference between type 2 and type 2b is that in type 2a, the chirality of the spinors in the NSR and RNS, for example, right, or in the Ramon sector, right, we have different chirality of the spinors, right. As a result, the supersymmetries that you get in the left sector and right sector have opposite chirality. Okay, I said 16 supersymmetries come from the chirality projection, right? And because all the fermions in the left sector have opposite chirality compared to the fermions in the right sector, the supersymmetry generators themselves have opposite chirality. Okay? So 1, 1 basically reflects that. One of one chirality, one of the other chirality. In type 2b, on the other hand, the Ramon sector carries the same chirality in the left and right. That is the difference between the Nevu-Schwarz and Ramon, the type 2 and type 2b. Right? It has the same. So the vacuum, right? The GSO projected vacuum. Let me remind you, the RR vacuum is AB into A, into B, and A B dot, A dot B into A. By convention, we always take the right sector to have the same chirality. Okay. Then the left sector will have A or A dot, depending on if it's 2B or TA. Okay. So because in 2B, both supersymmetries carry the same chirality, we call this 0, 2. Right? The supersymmetries of the same chirality, two supersymmetries of the same chirality. Okay, so whether it's Mn, right, will refer to M of what? One chirality, N of another chirality.
The statement that in target space the real supercharges are right. One is Q alpha, one is Q beta dot, and
something, yeah, exactly. Yeah.
Whereas both are Q alpha, Q beta.
Exactly, yeah. Yeah. Except that this alpha beta, of course, has to be, I mean, understood in the SO9, 1. Yeah, 16 dimensions. That's exactly.
They vary over 16 components.
Exactly. Pardon?
Like the fact that it's 0, 2 and not
2, 0, that's just a convention, yeah. I mean, 2, 0 will be equivalent. I mean, you could have taken both to be A dot, B dot, right? That's equivalent to having AB, right? Because what to define as positive chirality and negative chirality, right? That's up to us. Okay, but once that definition is fixed, then there is a difference between 2 and 2.
Also write 1, 1 subscript to it. What is that?
I don't know who writes 1, 1 subscript. What? Kirit says 1, 1 subscript 2. I see. I don't know.
2, 1 plus 1.
Is it okay?
Is it easy to see from here whether this is extended SUSI or
Yeah, n equal to 2 means extended SUSI.
can figure out the central charge by this one?
Yeah, not from here. You have to go to interactions and all, the supersymmetry algebra, right? But the fact that it's extended, you can already see that it's because it's n equal to 2.
So it would have just been 0, right?
Even then, we'll call it n equal to 2.
Yeah, n equal to
We call this extended supersymmetry, right? Once you have more than the minimum.
sheet theory will tell you what the sets are.
Yeah, yeah. Because worldsheet knows everything, but in a somewhat hidden way. Pardon? Yeah, because central charge will be given in terms of the various other charges of the theory. Right? Various other brain charges that you can work out what it is. No, typically once you fix the algebra, right, in terms of quantized generators, then loop corrections don't change it. When you compactify? Yeah, then it will be more. I mean, it will be, because if you take an n equal to 2 supersymmetric theory in 10 dimensions and compactify, right, the number of supersymmetries will be more. Not the number of supersymmetry generators, but what it is in terms of the minimal supersymmetry will be more. Right? For example, here we have 16 plus 16, 32 supersymmetries, right? Okay. If you compactify on a torus, all 32 supersymmetries are still there. Okay. But if you compactify on a 6-dimensional torus, okay, then it's a 4-dimensional theory, 3 plus 1 dimensional theory, right? In 3 plus 1 dimensional theory, a minimal spinor dimension is 4. Okay. In that case, the compactification will not change the number of supersymmetries. So you get effectively n equal to 8 supersymmetry. Because 32 supersymmetries will be counted as n equal to 8 supersymmetry in D equal to 4. Is this clear?
But you can compactify on something complicated to break all that.
Yes, you can. Yeah. I mean, even you can preserve only part of the supersymmetries. Like, for example, this theory, if you compactify on a Calabi-Yau manifold, right, it only preserves 8 supersymmetries, which will be n equal to 2 in 4 dimensions. For n equal to 4, you can compactify on a K3 times T2. Right? K3 is a 2-dimensional, 4-dimensional Calabi-Yau manifold. Right? So K3 times T2 will break it to n equal to 4. No, there are other choices. If you take, for example, this theory and do an orient default, which I'll discuss later, type 1 theory is basically you start with 2b and take a Z2 quotient, which exchanges the two left and right sector on the world sheet. Right? That will basically that you can see will break the supersymmetry into half, right? Because you are saying the left and right you are identifying, right? Quotienting means they are identifying, right? So they are not independent supersymmetries anymore, right? Because you identify the left and the right. So that gives you 16 supersymmetries in 10 dimension, which when you do toroidal reduction will become 4 supersymmetries. Sorry, 8 supersymmetries. Sorry, not any 8 supersymmetries, n equal to 4 supersymmetries, 16 supersymmetries, which is n equal to 4. Yes. That's why when I said the minimal number is 4, right? If we had counted this other way, right, you would have gotten 2-dimensional spinor, right? So here you are getting 2 to the 2, right? Not 2 to the 1. And that's because you have only Majorana. You cannot impose Majorana and phi together.
Hi.
Yes?
Can you hear me? How do you see? Well, I don't know whether you will be going to talk later in your course, but can you
Your voice is
say some?
becoming slow. Can you speak a little louder?
Can you hear me now?
Yeah, I can hear you.
Yeah. How did you see how many supersymmetries are broken when you compactify on torus or other Calabi-Yau? Will you be going to
That
talk
we
about
didn't
it
discuss
later?
because basically what happens in compactifying on a torus, essentially what it does is it identifies X as by periodic identification. Right? So using that, you can show that a periodic identification of X really has no bearing on the spectrum. The same kind of symmetries that are there before compactification will also be there after compactification. It's harder to see why, for example, a Calabi-Yau 6-dimensional Calabi-Yau manifold breaks it into quarter of the supersymmetries. Right? But that analysis is more complicated, but one can show this.
Okay.
But for torus, because it's just a periodic identification, you don't really do anything to the supersymmetry.
And if I compactify on a sphere?
You cannot even compactify on a sphere because that will not satisfy equations of motion. Right? The Einstein's equation has to be satisfied. So you can only compactify manifolds which which satisfy equations of motion. Equivalently, if you recall the string compactification, you can only compactify by thinking of this as a set of x's and product and take the multiple product to the conformal field theory, 2D conformal field theory. Okay. Now, a world sheet theory with target space as a sphere is not a conformal field theory. Okay, this you can check. It has a non-vanishing beta function, so you cannot compactify on a sphere.
You mean flat metric is required?
Pardon?
You want to say that you need the internal space to be flat?
No, not necessarily. Calabi-Yau doesn't have internal space flat. K3 is not flat, no. It has to be Ricci. To leading order, it has to be Ricci flat. Because Einstein's equation is R mu nu equal to 0, right? Yeah. Okay. So K3 and Calabi-Yaus are Ricci flat.
Oh, the Riemann is not.
Riemann is not 0.
Sphere is not.
Sphere is not. Sphere is not TC flat. T6 is flat. That's why you can compactify on T6.
It's completely flat.
Completely flat, yeah. Exactly.
The P6 is also in Calabria.
This is also a Calabi-Yau, yeah. Special case of a Calabi-Yau. Okay, the other thing I wanted to discuss is that we had imposed GSO projection, right? Because we had identified psi with minus psi. You recall that the GSO projection came because we said that in the field space, okay, if we have x psi psi tilde or x psi plus psi minus, right, we will make an identification of psi plus with minus psi plus and psi minus with minus psi minus. Right? That was the origin of the GSO projection. Okay. So I'll discuss briefly why we need the GSO projection. Okay, because this will also be useful. So need for GSO. So we'll see what happens if we don't have GSO, if we don't impose GSO projection. So the psi Lagrangian, worldsheet Lagrangian, if you remember, was something like this. In that worldsheet action is worldsheet. Is proportional to this. Okay, that's good enough for us. And this basically shows that psi plus has weight 0.5 and psi minus has weight half 0. Okay, where half this refers to u and this refers to v. Okay. Why does this refer to u and that refers to v? Okay, for that you have to recall. Pardon? The right refers to u.
That is the convention.
That is the convention, yeah. But let me remind you that where that convention came from, right? Because we had taken the continuation as tau goes to minus tau e, right? The Euclidean continuation, right? So in this case, u will become, which was tau minus sigma, will become minus I tau e minus sigma, and that is minus I times tau e minus I sigma. Okay. And this is what we had called W. This is in the bosonic string theory. Okay, this is what we had called the complex coordinate W. Right. So this basically is saying that it has, so this derivative with respect to V will become derivative with respect to W bar. Right? Because if U goes to W, V has a plus sign here, it will go to W bar. W is our convention right. Okay, holomorphic is right and anti-holomorphic is left. Okay. So this shows that it has, because if it is derivative with respect to W bar, okay, this is conformal invariant, this combination, right? Conformal transformation of V cancels the conformal transformation of del V. Okay. But this one, conformal transformation of this has to be cancelled by the conformal transformation of the psi pluses. Okay. So this has conformal at 1, so this should have conformal at half each to cancel it. Okay, well, this has conformal at minus 1, so this has to have conformal at half each to cancel it, and that's this 0.5. You can, yeah, you can. T psi OP. T psi OP will give, if you look at the expression for the T I have written down, right? I wrote the A length in terms of the size, right? From that you can work out the T psi OP and I will find that this is half. Yeah, everything is gauge fixed action. This is conformal gauge, right? We took the conformal gauge and then chi equal to 0. We set the gravity nose to 0. Okay, so our super conformal gauge. Okay, so it is in that gauge that it became a free field theory, right, on the world sheet. Okay, so this is clear, right? Psi has weight half, psi plus has weight 0 half, and this has weight half 0.
We need that case because only in that case the residual symmetry is.
Yeah, so we are always working in that case right now. Pardon? Light cone gauge is one of them, right?
Like one the super.
Yeah, there's an analog of light cone and super.
Well, mostly coming.
Yeah, so gauge decouple, and you basically said just like in the there you said tau equal to x plus, right? You have to use the also the similar gauge condition on psi plus and psi minus.
But we'll be doing BRST, right?
We'll be doing BRST eventually. You can also do light cone. Light cone is easy to, I mean, light cone has the advantage that it's easy to work out the spectrum.
So when
Because-
you do BRST, you have to reintroduce the chi, the gravity no, and then write down the full.
Yeah, well, I'll not do that. I'll just write down the BRST, the ghosts. Okay.
Without the.
Yeah, the same gauge. Chi equal to 0 gauge. Here I have not included the ghosts, right? Covariant gauge, you have to just now introduce the ghosts for BRST.
So we'll fix gauge.
Yeah, the gauge I'll still take to be chi equal to 0. Okay, so now Z coordinate was taken to be e to the w or e to the iw, which is e to the tau e minus I sigma. Sorry, e to the w. The I you have already taken out. So now we have this relation psi of z as psi of w dw dz to the power half because this half comes because it's the weight half. Okay, in the holomorphic sector, this is psi plus. So psi plus of w, put a mu index. So psi mu plus of w had an expansion of the form sum over n b mu n e to the minus nw. Okay, this follows from, I mean, I had an expansion in terms of u, right, e to the inu, and you can rewrite this in terms of w. So this basically tells us that in the w coordinate, so in the z coordinate, this has an expansion of the form sum over n okay, this minus half that you see here comes from this dw dz to the power half.
Right now you're not against it.
Pardon?
And
N, yeah, I'm not saying anything about what n runs over. Okay, that distinguishes between Ramond and Nebel-Schwarz.
Whether it's Z or Z plus half.
Whether?
Whether it belongs in Z or Z plus half.
Exactly, yeah. Okay. Now let's do the NS and R separately.
I think statement for psi bar with the, sorry, psi minus with the Z bar.
Yeah, exactly. Psi minus with the Z bar. I'm not going to do that, but it's the same statement to psi minus with Z bar. So in the NS sector, I had called this R, right? Let me change it to R. Just not to confuse. So this is somewhat R. In a sector, on the cylinder, it was anti-periodic. Okay. So, sorry, yeah, it was anti-periodic. So R was integer plus half. Okay. In a sector, R belongs to Z plus half. So we see that psi mu plus Z is single valued. Because here it gets shifted by half, right? So what does it mean? So imagine that this is a NS sector vertex operator. Using the same language as the CFT, right? The vertex operator at 0 creates that state out of the vacuum. If you have an NS sector vertex operator, and here, let's say this is origin. This is the origin, and here you have a psi mu of z. This psi mu of z correlation function with this will be a single valued function, right? Is that clear? In particular, this implies that the SL2R invariant vacuum. Yes, you record the convention that the states are created by applying vertex operators on the SL2R invariant vacuum on the Z, right? Suppose you didn't include any, put any vertex operator, right? Or identity operator. Then here you have nothing, right? And if you have nothing here, then psi mu better be periodic. That if you have nothing here, then there is no reason for psi mu to have any branch cut, right? Why psi mu should be non-single valued. Is that point statement clear? Yeah. Take the NS sector vacuum. Corresponding vertex operator is identity operator, right? So if this had been an identity operator, right, then psi mu of z should be single valued, right? Because there are no operator there, right? There is nothing special here. So that is saying that the NS sector vacuum, sorry, the SL2R invariant vacuum must be in the NS sector.
I'm just saying that for the SL2R invariant vacuum, psi mu should be single.
Psi mu should be single valued. Exactly. Exactly. And for NS sector state, psi mu is single valued, right? So the SL2R invariant vacuum must be in the NS sector, right? This you can also check explicitly. When you have all the oscillator expansions, right? You have given the expressions for LNs and GNs, right? Take those expressions, right? And see if the vacuum is annihilated by L minus 1, right? And what we will find is that the L minus 1 annihilates the NS sector vacuum, but not the Raman sector vacuum. So let me write this. So SL2R invariant vacuum okay, notice that I have been talking about NS without referring to the other sector, right? So you have already accepted that, okay, things factorize, right? Because you didn't complain, right? Because we can deal with psi plus and psi minus separately, right? So if we just look at the NS sector on the right, which is what we're dealing with, we learned that SL2R invariant vacuum is in the NS sector, okay? And I'll leave it as an exercise to check explicitly that L minus 1 on NS is equal to 0. Okay. And L minus 1 on the Raman sector is not 0. The Raman sector vacuum is characterized by the spinor index, right?
L tilde also, L tilde minus 1.
Yeah, so right now I'm only talking about the vacuum in the NS sector. I could have been dealing with NSR sector, sorry, RNS sector, right?
Only the
Yeah, so left sector, whether you are R sector or NS sector, plays no role in this.
bosonic string theory is vacuum. Why do we call SL2R? Isn't it SL2C?
SL2C. Okay, let's call it SL2C. If you use only the left sector, then it is SL2R, right? If you take the product of left and right, yeah, then it will become SL2C. So in the Ramon sector, psi mu plus of Z has branch cut at Z equal to 0. Right? Because the expansion, R is integer. Okay, so in the Z plane, it's half integer expansion. So it must be having a branch cut, branch point. Okay, so there's a branch cut going from here. So if you take a psi mu of Z here, by the time you come back to here, it become a minus sign. Okay. So now take two Ramon sector vertex operators which are close to each other. Okay, let me call it VR and VR prime because they need not be the same vertex. VR and VR prime. And look at a psi mu Z here. So this one has a square root branch point at this point and also has a square root branch point at this point. Right? Yes.
As you were saying when you were constructing the spectrum, that there are hidden ghosts acting on the vacuum to create the SL2R invariant vacuum.
Yes.
It's not just identity acting on the.
Yeah.
So we can't quite do this argument.
You can. I mean, you can just do it. I mean, the hidden ghosts you have not seen so far, so you can give this argument, right? I mean, you should have made this complaint long time ago, right? You are doing all the analysis without the hidden ghosts.
Directly say that NS sector vacuum is the SL2R invariant vacuum.
SL2R is from the matter sector, right? You can separate because it's a product CFT. You can define the SL2R invariant vacuum in each sector separately, right? Otherwise, you could have complained about the SL2R versus SL2C itself, right? We are working in the right sector and just in the matter sector, right? No ghosts. Okay, so here this argument told us that if there is an operator at Z equal to 0, there will be a branch point singularity, right? But of course, by translation invariance, that even if you shift the operator a little bit, right? So any other point Z prime, then the branch cut will be at branch point will be at Z prime, right? Wherever you are inserting a Ramon sector vertex operator. We can always choose coordinates in which that point is at origin. But now you see that if we go around these two things together, then there is no branch cut. Right? Then it will not change sign. So this along this contour is periodic, is single valued. Yeah, you had.
So you put two vertex operators on the plane.
Yeah. So as a function of Z, there is a square root branch point at 0.
Square branch point only at 0, right? Is there equal to, oh, okay.
Yeah. This 0, this is Z prime. So there is a square root branch point at 0 and a square root branch point at Z prime. Because I am putting also a Ramon sector vertex operator here.
Oh, which is constructed out of size.
Which is constructed out of size, meaning the same Ramon, maybe a different Ramon sector vertex operator, but it's a Ramon sector vertex operator. So if this was not there, there will be a square root branch point at Z prime.
Okay, so then basically you're saying that there is a cut between these two.
Yeah, there is a cut between these two. Or I mean, even if you take the cuts like this, doesn't matter. You'll change my chain sign here and chain sign back here.
Yeah, but that's just this cut. Right?
Yeah, that's just this cut, exactly. Right? So effectively, there's a cut between these two. Right? So along this contour, it's single valued. Is that clear? So this is saying that the operator product of two Ramon vertex operators is in the NS sector. Right? Because in the Z prime going to zero limit, we can use an operator product expansion. Okay? Think of this as a linear combination of vertex operators with appropriate coefficient. And those vertex operators must be in the NS sector. Because NS sector gives single valued psi. Ramon sector would have given double valued psi.
Product of two vertex operators, two Raman sector operators, the NS sector.
Exactly. So OP of two R sector vertex operator is in the NS sector.
But 3 is in again in the R.
3 is in R. Is this clear? So this is saying that if you are trying to build a theory, you don't have an option of keeping only the R sector vertex operator. That is inconsistent because you bring two R sector vertex operators together, you get an NS sector state. This you could have also said from the space-time viewpoint, right? If you have only spinors, right, then two spinors collide, it better produce a bosonic state, right? A vector-like state. Just from the spinor, the SO9, 1 algebra. Okay. So two Ramon sector vertex operators give rise to NS sector vertex operator. So we have to include the NS sector. Right? There is no option of not including NS sector.
But it just stay within the NS sector, right? Because the NS sector will never take it.
Exactly. So at the level of the OP, you can stay within NS sector. Okay, so which basically means that on the plane, okay, you may be able to, we can in principle define a CFT by only keeping the NS sector states. Forget about the Ramon sector states. So on the plane, okay, and if you want to combine left and right, basically it will say that with NS sector states, you are okay. You can, OP closes, right? Because product of two NS sector states will give an NS sector state. Is this okay? But this means that on the cylinder,
Branch points on the Z plane are always square root branch.
yes, always square root branch points, right? Ramon sector gives a square root branch point.
This is because the weights are always half.
Yeah, because the weights are always half.
But if you had a higher derivative, is it possible to make the weight like 1/3 or something?
So derivatives will not make, it increases the weight by integer amount, right? So derivatives will not do very much. Well, yes, from a space-time perspective, so this fact, this is a purely CFT statement, right? But from a space-time perspective, we can view it in many different ways, right? Indeed, Ramon sectors are Grassmann odd. So product of two Ramon sector, if you collide two Ramon sector states, it should give a Grassmann even state. Right? So the fact that two NS sector, two R sector will merge to give an NS sector state, you can see it from a space-time viewpoint. But this is a purely CFT statement. Okay, just as a CFT, you have to include the NS sector states are must.
But that has nothing to do with the order of the branch point, right? even if these two were 1/3 branch points, it still connect with the branch cut, and then this argument will be valid. That
No, then it has to be 1/3 and minus 1/3, right? 2 1/3 would have given Z 2/3, right? Then you have to merge 3 of them. But any twisted state, right, which produces branch points, right, you cannot work within that sector. Okay, it will always take you out of that sector. Right? If you had a 1/3 branch point, for example, then 3 of them will merge together to give a periodic set, right? Will give a single valued operator. So NS sector you have to include, right, from the perspective of the plane.
But when you have these 2D CFTs where you have fractional dimension of primary, like some of these minimal models and rational, can you, Ising model or something, Ising will half of it. But if you have this, can you represent them in these boards and then they'll have some.
Yeah, so the point is if you take the Ising model and represent it as a free fermion, right, psi mu has branch points. But psi, so you exclude psi. I'm not saying that you cannot include Ramond sector states, right? But you have to include NS sector states. Identity and the epsilon, the energy operator is also NS sector. That is okay, but on two sides, that is, I mean, that 1/16 is like a conformal dimension, right? So that's not a problem.
The fact that, but NS sector field should have integer moding.
No, no. Integer moding of what? Psi.
Yeah, whatever field.
Yeah, but that psi is not measured in the conformal way. Conformality is measured by T, right? Yeah, and it's an interacting theory. So, I mean, the conformalities just don't add.
But in the OP, it should make sense, no? Like if I take two half field.
Yeah, so the energy operator is basically psi bar psi, right? Psi bar psi is half, right?
Yes.
And you take the, okay, in fact, you have to take the projection, right? So energy operator actually eventually has dimension half. Yeah. Yeah, okay. Okay, but right now we are doing free field theory, so there is a confusion, right? But the fact that you have to include NS sector states, right, means that from the cylinder viewpoint, you have to include antiperiodic boundary condition. Is this clear? Because NS sector was antiperiodic, right? It had half integer, the R was half integer in the NS sector, right? So in the W coordinate, it's antiperiodic. So because of this, the torus becomes complicated. Because torus is like a cylinder that is whose two ends are joined together, right? You take a cylinder and identify the two ends, that becomes a torus. Now we are saying that along this cycle, we put antiperiodic boundary condition. Okay, because the cylinder is propagating, so they are antiperiodic boundary condition and are joining them together. On this cycle, you may make a choice. On this cycle, but whatever you do, you can show that if you want to maintain the full diffeomorphism invariance on the torus, right, which basically allows us to take linear combinations of the cycles to each other, we have to include all sectors. So imagine that we put periodic on this cycle. Okay, antiperiodic on this and periodic on this. What would go wrong? On this cycle, you have to put antiperiodic, right? Because that is a cylinder cycle, you put periodic here, right? So what would go wrong with this prescription? Yeah, modular invariance, because on the torus there is a diffeomorphism which you can change. If you take the torus, right? Imagine that torus you are describing it as a square, okay, where this is sigma 1, this is sigma 2, and you are saying that sigma 1, sigma 2 is equivalent to sigma 1 plus 1 sigma 2, which is equivalent to sigma 1 sigma 2 plus 1, and which is also equal to sigma 1 plus 1 sigma 2 plus 1. This is redundant, okay, but because once you identify this is automatic. Right? So this condition, right, subject to this condition, you can make arbitrary general coordinate transforms involving sigma 1 and sigma 2, right? And those should be symmetric. So in particular, you can exchange sigma 1 and sigma 2, right? So sigma 1 prime equal to sigma 2 prime equal to sigma 1 is a symmetry. It's a general coordinate transformation, and it's a symmetry of this periodic identification, right? But if you make this, then this anti-periodic and periodic boundary condition gets exchanged, right? Here you are saying that in sigma 1 direction you have anti-periodic, in sigma 2 direction you have periodic. But if you make a coordinate change, right, then sigma 1 prime will have an opposite boundary condition than what it was for sigma 1. Is this clear? No?
And this cannot be anomalous or something.
No, so this symmetry, that means, is violated by this boundary condition. You don't even need anomaly, right? So this particular symmetry is violated by this boundary condition. That if we take, so what is it saying? That on the torus, imagine I try to pull the boundary condition, that psi mu plus of sigma 1 plus 1, sigma 2 is equal to minus psi mu plus sigma 1, sigma 2, and psi mu plus sigma 1, sigma 2 plus 1 is psi mu plus of sigma 1, sigma 2. Okay? Suppose you try to put these boundary conditions, right? That's what I said, that you put periodic here, right? Let's take P. Let's take this boundary condition. That corresponds to this. Okay. Then, if you extend sigma 1 and sigma 2, this boundary condition is not respected. Right? This becomes plus and this becomes minus.
That would just mean that psi plus is not invariant in sigma 2 transformation.
Not invariant under?
Transformation.
No, psi plus is a spinner, and these transformations you can check what it does to psi plus. It doesn't do very much. On the torus, right? It's just a plane, no? And you are just doing exchange.
Yeah, but in principle, something can transform non-linearly and
See, even if psi plus picks up a phase, it makes no difference to this, right? It will cancel on both sides. Something what? There's no other field, no? Right sector has no other field. No, it can't go to left sector. Okay, so basically this is saying that if we include these boundary conditions, anti-periodic, periodic, then you must also include periodic, anti-periodic boundary. Okay?
So, like, effectively, we are saying that we should have four combinations, all four combinations.
Right? Okay, let's see why. So, anti-periodic, periodic is not allowed. Not allowed, right? Must include, in this case, we must include PAP. What about this? This is allowed by this, right? Both minus signs is okay, right? something else goes wrong, because you also have a transformation where sigma 1 prime is sigma 1 plus sigma 2 and sigma 2 prime is sigma 1, sigma 2. Okay, this sigma 1 prime and sigma 2 prime has exactly the same identification. It just follows from the identification of sigma 1 and sigma 2. But now we have a problem, because if it's antiperiodic under sigma 1 translation and translation by 1 under sigma 1 and by under sigma 2, then it becomes periodic under sigma 1 prime translation. Okay, basically what I'm saying, okay, let me draw pictorially, right? We have this torus. I think it's easier to see in the picture than in equations, right? So imagine that we are putting antiperiodic and antiperiodic, right? Along these directions. Now what we are saying is that we can take our basis of cycles to be this. We can represent the torus in this way, call this as one cycle and this another cycle. Okay. Now along this cycle, okay, it becomes periodic, right? Where it's antiperiodic in this direction and antiperiodic in this direction. Okay. So along this cycle, we now have a periodic boundary condition and antiperiodic boundary condition. Okay. So if you this has a choice of basis, right, which is equivalent to making this transformation from sigma 1 to sigma 2 to sigma 1 from sigma 2 prime, then you get periodic antiperiodic.
Like I guess that was like S transformation and this is T.
Yes, that's like S transformation is like T. Okay. So then again you have to include the periodic antiperiodic boundary. Only boundary condition that respects this modular, that is a subset of all possible boundary conditions, and yeah, that respects modular inverse is PP. Right? If you start with PP, then there is a confusion, right? Any transformation that you make will keep it periodic. But PP means that you are allowing Raman sector states to propagate, right? In this channel. P is Raman, right? So because you are letting Raman sector state to propagate in this channel, right, then you have problem with on the plane. Okay. So this is basically saying that you cannot just work with Raman or Nebel-Schwarz, you have to include both sectors.
Not give up the torus.
Pardon? Yeah, you cannot give up the torus. That's a Riemann surface. No, you are supposed to sum over all Riemann surfaces. Fortunately, you don't have to do it for every Riemann surface. One can show that if you have a CFT and it satisfies all the consistency conditions for the sphere 4-point function and torus 1-point function, 0 and 1-point function, that's good enough.
The sphere you mean plane.
Plane, yes. Okay. So basically then that this is the reason why we cannot work with just NS and R. Right? You have to include, to get a good conformal field theory based on which you can formulate a string theory, we have to include Nebel-Schwarz and Raman sector states and combine them appropriately so that it's consistent with modular invariance. Is this clear?
Can I not demand that the theory should only be defined on the plane? Maybe
No, because string theory, then there are no interactions.
just
Even from the CFT perspective, the point is that often you don't have Lagrangian in the CFT. Right? So if you don't have Lagrangian in the CFT, then you have to find out the condition, you impose the conditions on the CFT correlation functions that all theories with Lagrangian will satisfy.
okay.
That's the definition of local CFT, right? A theory with Lagrangian. So if you have a theory with Lagrangian, which can be coupled to gravity, 2D gravity, okay, then it has certain properties. Modular invariance is one of them, right? Because if you had a Lagrangian and if you had a consistent coupling to gravity, right, then these properties just follow from there, right? Because you have diffeomorphism invariant theory, you have Weyl invariance. No, if you had a Lagrangian, which can be consistently coupled to the gravity, you can put it on a torus, right?
Yeah.
And it will have these modular invariance properties.
Yes, you can demand the same consistency condition for other theories which do not also have a Lagrangian.
Exactly, right? So the definition of a CFT, the way we give, is that it should satisfy all the consistency conditions that a Lagrangian theory, which can be consistently coupled to gravity, will have on any 2D manifold. Right? So you derive the properties from there. Okay, it's a constraint that you put because for other many purposes maybe you don't need it, but certainly for string theory you need it. And generally for CFT, when one says that you have a consistent CFT, that you demand all this. That even though you don't have a local Lagrangian, it should have all the properties that a theory with local Lagrangian will satisfy. Right? That's the principle.
I'm never coupling to gravity. I'm not demanding invariance on a torus. I'm just on the plane. I'll never go to a torus. That's still a consistent theory.
Yeah, it's a consistent theory. It's like an Ising model. You can have identity and the energy operator and not spin operator. That's a consistent theory. Because the OP of identity and energy operator never produces a spin operator. Yeah, that is like the NS and S sector, exactly. Identity NS and the energy are like the NS. Right? So, given any theory, right? If there is any CFT, if there is a Z2 theory, Z2 symmetry, you can just project out all the Z2 non-invariant states, and it's a consistent theory on the plane. That cannot be put on a torus. Exactly, right? So these theories are what are called non-local theories, right? That a local theory you expect you should be able to couple to 2D gravity, right? Because it has a local energy momentum tensor. So you just couple the gravity to the energy momentum tensor, right? That's the way you couple gravity to the theory. So if it has a local energy momentum tensor, then it should be, so that's the philosophy, that if it has a local energy momentum tensor, you should be able to couple it to gravity and hence get all the properties. So if you're not getting all the properties, that would mean that this theory doesn't have a local energy momentum tensor. So this is the need for GSO projection. And next time we are going to use both of these in a crucial way because we are going to describe heterotic string theory, okay, where we'll use crucially the fact that this spectrum factorizes, okay, and the fact that the GSO projection is needed, right? That even if you didn't have any space-time supersymmetry or anything, right? Here you could say, okay, space-time supersymmetry is a motivation as to why you should include the Raman sector. Okay? But in the heterotic string theory, that will not be the motivation. But nevertheless, right, the fact that you need to keep both Nemours and Raman, right, will be important because you'll use it. Okay, I think I'll end here. Any question? Yes. Oh, NS and R kept because of the GSO projection. Because you remember what was the reason for GSO projection? That we identified x psi plus psi minus in the field space to x minus psi plus psi minus and so on, right? Once you have done that, okay, you keep only states that are invariant under this projection and you include states that for which psi plus changes to minus psi plus as you go around the string, right? This is the NS and R sector, right? The fact that as you go around the string, you have to allow psi plus to be either periodic or anti-periodic. Right? Once you have done that, then the projection is automatic. You cannot do one and not the other, right? Because physically in the field space, you are identifying the. So what I said today, right? The need for including the Raman sector, right, is the need that you have to use in identification in the field space. Right? That's the statement that you have to use Raman sector. And once you have identified in the field space, then all states better be invariant under this identification. Right? So that's the GSO projection. So GSO projection and the different sectors always go hand in hand. If you have chosen a particular GSO projection rule, then that fixes what kind of twisted, what kind of sectors you have to include in the theory.
This is upon going around the cylinder.
Yes. Or going around the plane. So the reason that you can allow some psi to be antiperiodic on the plane, right, is because the psi and minus psi are identified. Right? That's the configuration space you are working in. So even though it looks antiperiodic, it's actually periodic. It's single valued because psi is just coming back to an equivalent point in the field space.
So if we do a different GSO projection, say we do in type 0 and 0, like GSO even adding both of the sectors.
Yeah.
Both of the holomorphic and then what would be the corresponding boundary condition?
Yeah, so there the boundary condition will either both psi plus and psi minus are periodic or both psi plus and psi minus are antiperiodic. Right? Because there the projection that you are taking is x, the identification that you are taking is x psi plus psi minus is x minus psi plus minus psi minus. This will be a type 0 theory. Type 0 theory has both signs reversed. Right? Not separate reversal in left and right sector. So both psi plus and psi minus antiperiodic or both psi plus and psi minus periodic. Exactly. So you don't have any antiperiodic periodic sector, right? Because here I have only dealt with the one sector, right? The right sector. So each cycle will be in type 2, each cycle will be labeled by how psi plus changes and how psi minus changes.
Antiperiodic on both, then we'll have to include periodic on.
Exactly. Exactly. Okay. But not all of these are allowed, right? So for that you have to check the modular invariance. Right? That's a more complicated analysis. This analysis only tells us what kind of sectors you have to include. Right? But at the end, you have to make sure also that the torus partition function is actually invariant on a modular transformation. Okay, that's a second order condition, right? Not just this physical picture, but the actual expression should be modular invariant. Right? And typically what happens is if you make an arbitrary choice, then the expression picks up some additional phase. Meaning, we said, okay, why not 5 of them as periodic and 5 of them as antiperiodic, right? This identification, right, we could have taken other ways also. Right? So one psi plus changes and different mu's. If you didn't worry about Lorentz invariance, you could do many things, right? Next time we'll not worry about Lorentz invariance. So you could do many things. We'll see why, because we'll use internal fermions to twist. In one of the sectors. Yeah.
So if we take this one, then we can probably calculate to see that the torus partition function will be
modular invariant, exactly. Right? That's why type 0 is a well-defined theory. Right? But we cannot do anything that we like with this.
Sorry, type 0 is defined on the torus or not?
Yeah, type 0 is a theory, well-defined string theory, right? Where the GSO projection rules acts simultaneously on psi plus and psi minus. Right? There is no individual action. The only problem there is that the actually one loop you generate a tadpole, and then you don't know how to deal with it. Right? But as a theory, as a string theory, it seems consistent, except that it doesn't have a vacuum.
But with the GSO projection, rule out the vacuum there also, tachyon there also.
Yeah. GSO projection will rule out tachyon there. Okay, no, I shouldn't say that. In some type 0 theories, right, in this non-critical type 0 theories, the GSO projection will rule out the vacuum. But otherwise, you'll have a vacuum. You'll have a tachyon.
But for the analysis of the spectrum in all these sectors, it will go analogously only that we'll have only a single GSO parity of it.
Exactly.
Like the right and
Exactly. Yeah, otherwise the analysis will be quite identical.
So whatever states we have in type 2 will always be there because
No, RNS will not be there in type 0. In NSNS and RR, what you are saying is true. Because the projection is less. Right? But there will be no analog of the RNS sector in type 0. Because you are doing simultaneous twisting of both psi plus and psi minus, right? So if you go around the string, either both psi plus and psi minus are periodic, or both psi plus and psi minus are antiperiodic. Applying oscillators doesn't change the sector, right? That only changes the GSO. Yeah. But RNS sector is just not there in type 0.
But if I declare the vacuum to have even parity?
Even then, RNS means what? Psi plus is antiperiodic and, sorry, so RNS is, yeah, psi plus, psi minus is antiperiodic and psi plus is periodic, right? Whatever. But that boundary condition is not allowed in type 0. Because if you see, you have to make sure that that as you go around the circle, right, you make this connection, right? You either do a minus sign or plus sign for both. Right? What you are trying to do here is one has plus sign, one has minus sign, right? That's not the same configuration in the field space. Not mode expansion, the vacuum, the sector, right? The sector is not present. Once you have a sector, then you talk about mode expansion, right?
I never have a RNS sector.
You never have an RNS sector in type 0, right? Or NSR sector. Yeah. What?
You mentioned party.
Around amplitudes programming.
Yeah.
Ashoke is coming, Chandra is coming.
Yeah, and Gautam is, originally you have
is
started
it.
thinking of Gautam's welcome party. It will also be Gautam's welcome party.
Yeah.
Oh, this
Will it be a surprise for too much?
What?
So when do you want to do it?
Yeah, so I don't know when Gautam is coming.
Yes.
Oh, he is here, I saw. Okay, see, this weekend I think he will go for, there is something going on at IIS.
yeah.
Some
8th
black hole.
and 9th there is two.
Yeah.
Weekend. No, but anyway, we wanted to do next week because
Yeah.
amplitudes.
Yeah, so let's do it sometime next week. I mean, if you are making pizza, it will be useful to have it on a holiday. Holiday meaning Saturday or something. Right? If you are getting food from outside, you can have it any day.
And we are going out or we are.
I think he offered.
No, I offered, but you can go out also. You can go to Pai or some other place. Right? I mean, they said, why not in our house? I said, okay, for me, this is not.
We are exploiting your.
Our house, there is a problem at all. Right? So that you can always have. It depends on whatever is most you think is most convenient, you can.
That one is more convenient because we don't have the hassle of booking some place, 20 people.
But here the one is everyone has to go there, right?
Anyways, everyone has to go somewhere. So might as well. Unless you have,
Okay,
if you are completely fine with that.
Yeah, I'm completely fine.
Okay, let's see.
You decide, yeah. You
And
decide.
Who's on?
You?
That's why we waited.
Okay, this is not a question to ask.